Were you ever sitting there playing your game and thought, how does this work? How can I play videos, run games, or browse the internet? How does your computer know what numbers are? Well, it doesn't store numbers like 7 or 42 in the way you would think. It's just tiny electrical signals that are either on or off. So how do computers turn ones and zeros, or on and off, into real numbers? Well, to answer that, we need to understand what a number system is. So what exactly is a number system? Well, it is a way of representing numbers using a specific set of symbols and a base. The base tells us how many symbols we can use before we move to the next position, and the set of symbols represents the current value in the particular base system. Easiest example of a number system that everyone knows is a decimal system, also known as the base 10 system, consisting of 10 unique symbols, digits 0 to 9. Each position in a decimal number represents a power of 10. For example, the number 265 can be written as 2 times 10 to the second power, as it's in the third position, plus 6 times 10 to the first power, as it's in the second position, and plus 5 times 10 to the 0th power, as it's in the first position. And that, obviously, since it's already in base 10, just sums to 265. A common number system you might have seen is called the hexadecimal. It's a base 16 number system, and it consists of numbers from 0 to 9 and also the first 6 letters of the alphabet. So an example of this is the number 1F, which you can convert into decimal by doing 1 times 16 to the first power, as it's in the first place, plus F times 16 to the 0th power. Or you can rewrite this as 15, as you know this is the 15th number, and that is 31. Now that takes me to binary. Binary is a base 2 system that consists of symbols of either 0 or 1, on or off, low or high electrical signals. Now here is a binary number, and the way you would represent this in binary to decimal is you would take, again, the first number, so it would be 1 times, since it's a base 2 system, 2, to the place it is, minus 1. So this is 0, 1, 2, 3. This is the third place. So you do 3 minus 1, which is, it's the fourth place. So 4 minus 1 is 3. And the same for the rest. And you would get 14. So you can represent 14 in binary as this number. An easy way to remember how to convert any base n system to base 10 is know that it would be AX. So A is any value that you're currently on. So if it was, for example, this number that we just had, this is your AX. This is your AX minus 1, AX minus 2, and so forth. So it would be that value that you have there times your base. So before, for the binary number, it was again 2, to the place it is. So in the number that we had before, this was your x place, so it'd be whatever place this is minus 1, and add that to ax minus 1, so this number right here, times n to the x minus 2, so it'd be x minus 2, and you do that all the way until the right side. And that's how you convert any number and any base to base 10. Now that you can convert between integer decimal systems and binary numbers, we have to talk about signed and unsigned binary numbers. So here's an example of an unsigned number, 1111, which is also 15 in decimal, and this is always a positive whole number. Now we can look at the signed counterpart, this one right here, and this number is -7. Now you might be asking yourself, how is two numbers that are written the same exact way completely different? Well, the way signed numbers work is the leftmost digit, the most significant bit, is either 1 or 0, and 1 represents negative numbers and 0 represents positive numbers. So if I had a 1 here this whole number would be a negative number. If this was a 0, this whole number would be a positive number. And the right numbers, these numbers right here, are how I showed you to count numbers before. So if this was, let's say 0, 0, 0, 1, then this number is positive 1. However, if I change this 0 and if I put a 1 here, then this number would be negative 1. And that's the difference between signed and unsigned binary numbers.